Assalamu alaikum, my dear students. How are you? Hope you will be in the best of health, wealth, and happiness. I welcome you all into my today lecture. Today we are starting the new unit 18, Dawn of Modern Physics. I'm your teacher, Muhammad Ikram, and I welcome you all into my today lecture. So let us start with the name of Allah Almighty. Or the since there is no connection between the last chapter and this chapter, so I think a review is not that much important here since we are all starting new. Now our today topics will include introduction to modern physics, reference frame, and the spatial theory of relativity, STR, and the consequences of the STR. We will discuss all these in our today lecture. Introduction to modern physics. Now, what is modern physics? Before, can a physics be modern or old? This is a very strange thing, right? Uh, Let me explain this to you in a way that I think be best to start from the Newtonian or classical physics. The classical physics are the Newtonian physics. That is, the classical physics or the Newtonian physics is the physics that is the last till the end of 20th century, right? That last till the end of the 20th century. Okay, so that is the called the classical physics or the Newtonian physics. The classical physics or the Newtonian physics works the laws of Newtonian physics are classical physics. Classical physics work works best under the framework of, under the effect of, number one, that is at the microscopic level. At the macroscopic level. Macroscopic level, that is, for example, the heavenly bodies, right? Or when you consider bodies individually, right, as a single entity, then the Newtonian physics or the classical physics work best, right? And that is that the laws are inconsistent and they can explain any phenomena very clearly. There is the second important point, that the laws of physics work best at low speed. That is when the motion of the object can be best explained by the Newtonian or classical physics when they are at low speeds. For example, you can explain the motion of the aeroplane best, right? Because that is, in physics, that is considered to be relatively at low speeds, but particles such as muons, pions, or like that, there it is very difficult to explain the motion of those particles by applying the simple classical mechanics physics, the classical mechanics laws to them. So the classical mechanics work best at low speeds, right? And that is, and at low temperature, and at relatively higher room temperature, high or room temperature, room temperature, right? The objects work best, their motion or their state or effect can be best explained. The Newtonian or the classical physics, usually the Newtonian are classical physics, the Newtonian or the classical physics contains they contains the basic Newton equations, basic Newton laws or equation. There is the Maxwell equations, yeah, the Maxwell work, and thermodynamics laws and thermodynamics laws, which work or which can be which are applicable in the conditions they are given here, that at the macroscopic level and at low speed and at relatively higher temperature or room temperature, they work best. So this is known as the classical physics or the Newtonian physics, while contrary to this, the modern physics, the 20th century physics, the physics, modern physics. Now, what is the modern physics? In a simple word, like in English, I'd like to tell you that this is a kind of up to date physics. Up to date physics. So, what does really this up to date physics mean? Right? It is not like we say in our that is in routine that this software or this thing is up to date and this is not. It is something different for us. In fact, the first of all, the modern physics starts from the point where the classical mechanics fail to explain certain phenomena. Yani, that is the, I would like that the beginning of the classical physics is in fact the failure of the classical physics. Yeah, classical physics are the Newtonian physics, right? And those failures are those failures consist of the first one, for example, look, that the classical physics fails to explain the motion of objects, the motion of objects at very high speed. What? At very high speed. At very high speed, such as nearly the speed of light. Nearly the speed of light. Nearly the speed of light. And here the result produced is totally different, right? That is that even that when objects move, then this motion can influence other physical quantities which the common senses do not accept. For example, I would like to tell you that motion affect time, right? So this is something very strange, that whether time can be affected by motion. So this is what really our mind do not accept, but for the physics it is true, and indeed it happened and experimentally proved. So the laws of classical mechanics fail to explain this phenomena. So we would look towards more better understanding and more comprehensive laws and higher mathematical forms to explain such phenomena. Second, there is the motion of objects, the motion of the objects at microscopic level, at microscopic level. For example, the motion of the gas molecules or particles together, right? So the classical mechanics does not have very clear understanding to explain the motion of particles at the macroscopic level. And the third failure of the classical mechanics is that the study of objects, yeah, the behavior of objects, better I would write the behavior of the objects at extremely low temperature, at extremely low temperature, at extremely low temperature, such as nearly absolute zero, nearly absolute zero. And the world of those particle objects or substances completely respond in a different way. And here at this point, I would like to give you the examples of, for example, if you remember, I told you about superconductors, that superconductors provide zero resistance at extremely low temperature. This is the kind of effect which the classical mechanics fail to explain. In no way the classical physics or the classical electrodynamics can explain this phenomena. So this is one of the reason where the classical mechanics fail to explain these phenomena. This leads to a more comprehensive study, right? And the scientists started working on it, how they can explain these phenomena in such a way that the theoretical and the experimental results coincide with each other, right? That they support each other. So the classical mechanics, the modern physics, tools of the modern physics, tools of the modern physics, tools of the modern physics. The modern physics, right? They work by using the quantum mechanics. Now, no classical mechanics or Newtonian mechanics. The quantum mechanics, the that is the quantum mechanics, the STR and the STR and the GTR, special theory of relativity and the gravitational theory of relativity. So modern physics use these tools to explain the leftover of the classical mechanics. Moreover, I would also like to extend my idea to that is right, because there are still more points I would like to add to it, because they would be coming in your book. So that is what I want to add to more to the failure list, right? As I told about the low temperature, the small distances, that is the motion of the particle that is at extremely small distances, such as on the nuclear scale, on the nuclear scale, right? And the as I told, that is that the on the nuclear scale, right? There are other effects also. For example, the black body radiation, the BB radiation, the black body radiation, the photoelectric effect, the photoelectric effect. That is, the photoelectric effect is the interaction of energy with matter. which is beyond the framework of the classical mechanics. Interaction of matter, oh sorry, the interaction of energy or radiation with matter. So that is what the classical mechanics fail to explain. Similarly, we have the Compton's effect. No need to explain them right now, right? Just I'm telling you the effect where the classical mechanics cannot work. Pair production, pair production, and annihilation process. Pair production, these are the few examples where the classical mechanics fail to explain. So as I told, or the classical mechanics fail to explain in these scenarios or in these circumstances. While as I told, the quantum mechanics, that is the quantum mechanics are the special of theory of relativity best to explain, that is the motion of objects, motion of the objects at very high velocities, at very high velocities, at very high velocities, small distances, small distances, and even at the microscopic level, the motion of the particle in bulks, the microscopic level. So these are the few important points where the classical mechanics fail to explain, and so we look to a kind of an up-to-date physics. That up-to-date physics we call the modern physics. Now we have the frame of reference. Now what is reference frame? Yeah, frame of reference. Reference frame. A reference frame. What is reference frame? That is, it is the coordinate system. It is what? It is the coordinate system. It is a coordinate system in which measurements are made. I'm explaining this to you, okay? Or we can say that the place from which motion is observed and measured. The place from which the place from which the motion is observed, the motion is observed and measured, the place from which the motion is observed and measured is called the frame of reference. Why we need the frame of reference, right? We need the frame of reference because I would like to take your attentions towards a very interesting situation, right? For example, object may have different, the reason is that this is the reason for the having the frame of reference, that objects may have what? The object may have different velocities. The object may have different, the object may have different velocities, relative to different positions, relative to different circumstances or position, that we call different frame of reference. For example, a man walking on the floor of the train has a different velocity with respect to his seat and with respect to the ground. For example, let us see that I would like to give you the kind of example here. For example, let me choose that we have this as the road, for example, right? As you see, look, this is, for example, the road. And let us suppose, for example, I choose that we have the, look, that we have, that is the, let me make a kind of like this is, see here, look, for example, we have, that is, let us suppose, for example, we have the bus example I would like to give you, right? And before I told train, but I cannot rather train here, right, in a hurry. So let me choose this bus, okay, as I'm doing it here for you. Okay, let us suppose, for example, as you see, the bus is moving in this direction, right? Let's suppose, for example, here is an observer, and the observer is watching the motion of the bus. See here, we have the observer here. Here is an observer, right? And let us suppose, for example, the observer watch stand here. This is the observer. Is it the observer A? Is it at rest? Here you see. Now there is, this is, let's say, the floor of the bus, as you see here, right? Now look, the bus is moving with a speed of 90 kilometer per hour in this direction, right? If I just even choose the direction north, east, west, and south, as you see. So look, the bus is heading towards east with a speed of 90 kilometer per hour. Now suddenly a man left his seat. This is what the seat of the man, right? He leave the seat and he stands and walk in a bus, right? Let me choose this as the man. Here you see that the man walk here. I'm so sorry for this. See here, the man just get off his seat and let's say walk here. This is the man, and the man walk on the floor of the bus with a speed, let's say 3 kilometer per hour. So here, look, there are two kinds of the speed. For example, the speed of the man and the speed has a two, the man has a two different, in a two different scenario. For example, the speed of the man 3 kilometer, yeah, 3 kilometer is too much, 2 kilometer per hour, 2 kilometer per hour when walks on the floor of the bus. So with respect to his seat, the main speed is what? The main speed is 3 kilometer per hour. For example, if I tell you that a man is moving at 3 kilometer per hour, so this cannot describe the motion of the man be completely, right? Why? Because there is something lacking, right? The man does not have the speed of 3 kilometer per hour. I cannot say it like this. And what I would like to say is the speed of the man or the passenger is 3 kilometer per hour with respect to his seat, but his speed is 90 kilometer per hour with respect to the ground. This is what? This is ground with respect to, with respect to the ground. So this is why we need the frame of reference. So here the observer frame of reference is at rest, right? And here for there the frame of reference is moving, right? The moving frame of reference. So as I told, that frame of reference is in fact the coordinate system, right? It is what? It is a coordinate system in which measurements are made. So as you see, look. So here, this is the frame of reference of the man, right? Which consists of the x-axis, y-axis, and the z-axis. And this is called the origin, the point from where the motion of the body starts. Similarly, we have the frame of reference with respect to the seat also. So you see here, there is a moving frame of reference and there is a rest frame of reference, okay? So frame of reference is in fact a coordinate system in which measurements are made. Now, the types of the frame of reference, types of the frame of reference, frame of reference. The types of the frame of reference. One, we have the inertial frame of reference. The inertial frame of reference, or this is also called the non-accelerating frame of reference. The non-accelerating frame of reference. The non-accelerating frame of reference. So here in the non-accelerating frame of reference, the frame of reference in which which is at rest, yeah, stationary. Stationary, for example, here this frame of reference is stationary, right? Or which is at rest, or having uniform motion, or having uniform motion. The frame of reference which has what? Which has the uniform motion. That is simple. I would like to say that the frame of reference which has zero acceleration by all means, right? So normally, look, we usually take the, for example, aeroplane traveling at a constant, moving at a constant speed. That is the bus stop. That are the example of the inertial frame of reference. The non-accelerating frame of reference are the non-inertial frame, non-inertial frame of reference, non-inertial frame of reference. Non-inertial frame of reference are what we call accelerating frame of reference. Accelerating frame of reference. Frame of reference, that is where acceleration is not zero. For example, the take off of the aeroplanes, the landing of the aeroplanes, and that is the turn of the aeroplanes. These are the examples of what the non-accelerating frame of reference. So these are our two frame of references, and we would need them down the road. Now, that is the I would like to explain to you that is the to explain to you the relativity. 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 But before explaining relativity, I would like to tell you that there we have two quantities, right? That is one we call the absolute quantities, physical quantities, the absolute physical quantities, and one we have the relative quantities, the relative quantities. For example, absolute quantities are those quantities which motion, yeah, which status is independent of others physical quantities, while relative quantities which depends what which depends on other quantities, right? For example, which you need in order to explain them, you need other quantities also. For example, look, in the past we thought that time is absolute. We do not need any other parameters, or there is no other physical quantity which can affect time, and we consider that time is absolute, right? But now in the modern physics, it is not like that. Time is relative, motion is relative. Why? Because, for example, motion can be affected by events. Yeah, time, that is, the time can be affected by the motion. So they are independent, they affect each other, so they cannot be termed as absolute. They are called relative quantities. Similarly, for example, I can explain your motion with respect, for example, the motion of the aeroplane with respect to the airport. We say that the airport is stationary, and this is why we can say that the aeroplane is moving. So we explain the motion of the aeroplane relative to the airport, and this is how possible, this is what possible that we can explain the motion of the aeroplane. But look, for example, if by some means, if we make us in an observer unconscious, and if we allow the person, the observer, to be on the train in a way that he does not know what was his initial state, and the train is such that it all there is a special yeah, the train example would, I think it would be best that, for example, if we have a train, and the train compartment, we have a compartment in the train, and it is in such a way that it has all electronic doors, windows, and they are all closed in such a way that you cannot see the outside world, right? Now, there is, once the man is unconscious, and if the train start motion, and the motion is such that it is highly uniform, no change of speed, no change of direction, nothing else. Now when the man become conscious, and when you open the window to the man, then the man would be unable to explain his motion. Why? Because he do not find any such relative position or circumstances to which he can explain his motion, right? He cannot say whether he is at rest or whether he is in motion, right? So this is one of the reason. But suddenly, because the, to him, he may be considered that he is at rest and the outside world is a what, in motion, right? But in fact he is actually is in motion. But when the train slows down, or when it start increasing its speed, then definitely he will feel it. So there is no way to detect the motion, or to detect the motion once there is what, once there is when we consider things as absolute. So relative quantities are those quantities which can be affected by other events. So time is relative, motion is relative. Now in there is the in relativity, before relativity, for the I would like to tell you, like for example, in the Newtonian physics, the Newton physics in fact took us to the moon, while the relativity, I would like to tell you that is such a great science, and such a deep and an interesting science, that one day this theory of relativity, or this relativity alone, will point us to stars, right? We will be able even to travel to stars, maybe not today, but maybe in the future. So before the relativity, before STR, people thought stars are in fact beyond our reach. But now we think that we can reach them one day. Distance is relative, as I told, depends on motion, right? So that is how the relativity is. And in fact, that in a frame of reference which is nearly moving to the speed of light, the distance in fact contracts. So you see that, look, the distance is affected by the motion, so distance is relative. Time stretches during the situation for an particle where are the body which is moving nearly to the speed of light, and the time stretches enough that can allow the future astronaut to access to stars and beyond. So that is how the relativity is in fact. So the absolute motion, as I told, that Newton suggests that motion is what? Motion is a relative. And the before this, the Maxwell laws, actually, they were of the opinion that motion is absolute. But when Einstein came, then Einstein put forward the idea of space and time, and they said that space and time effects can greatly be affected by motion. So that is what I would like to explain this in a way that we only change our position when we move, right? This is what classically we can say, right? That is what, but in the Einstein opinion, when we move, we also change our rate of proceeding into the future. So you have seen that our motion has affected the time. So time is relative. So that is what the result of this statement is, that proceeding into that future is in fact that time is altered, right? So time is not relative, it is not absolute, it depends on other quantities also. So this is the today lecture. Unfortunately, the time is already over, and then I would like to start my next lecture from the STR, the postulate of the special theory of relativity, which Einstein put forward, right? And we will go on with this, and the consequences of the relativity we will also explain, inshallah, in our next lecture. Okay, so see you there in the next lecture.